do this talk because how many people actually here have ever directly worked with, I guess, Ruby's like thread class or like the process class? Yeah. So I've done like a little bit of it, but I really want to do this talk so that I could like force myself to learn. So this is kind of like an intro to programming with Ruby threads. About me, my name's Braden Schaefer. I work at 500 Friends. It's a loyalty platform. They're based in San Francisco. I've been working with Ruby for 6 years, and that's my GitHub if anybody's interested. So for those not familiar, what are threads? Basically, they allow us to run snippets, functions, code blocks in parallel, like side by side. We can do this in all Rubies. In all Rubies, one thread is backed by one OS system thread. So I imagine, I'm not like 100% sure how that works, but I guess like there's system schedulers in a CPU. There could be like, if you have 8 cores, I believe that's like 8 schedulers. So like the max concurrency or the max you're going to get out of that is about, like the most efficient it's going to be is about, I guess, 8. You can run like thousands of threads, but then you might be overloading your system. And they also share the process state, which is the memory, with the thread that spawned them or created them. So let's see how they work. Can everybody see that? So we got a function up here we're just going to log sleep before we sleep. We're going to say we're about to do it. We're going to sleep for a second, and then, well, that's a typo. Then we're going to say we're finished. So what we're going to do right here is kind of log what we're doing. Here we're going to call just Ruby, straight Ruby function. In the next block, we're going to send that same function to a thread, and we're going to see what the output is. And I don't know if you can notice this, but you can see here's our Ruby function calling the sleep method. It's sleeping for a second, just like we expect, and then it finished sleeping, and then we get this output right here. It's done. And now we're going to enter the threaded version. We're starting a thread, and we already get the output that we finished starting the thread. Our code actually has not even started to run because we don't see any output. And we actually make it to the very end of our program before the thread has even started this output. We call thread.join because that tells the current process to wait on the thread that's being run. And then at the bottom, we can see that our code is finally ran. So what's happening is the thread is executing our sleep function in the background. I already explained that here. Yeah, so that's exactly what I just said. So here's an example of things like really doing things in parallel. The first block is just Ruby. We're going to first log our start at that time, see how long it takes us to sleep for basically 5 seconds, 5 times sleeping. So it's going to sleep for 5 seconds, and then we're going to see how long it took to run this little program right here. And then we're going to do the thread version. We're going to log the fact that we're starting our thread program. We're going to spin up 5 threads, and that thread is going to sleep now for 1 second. So we're sleeping in CPU time for a total of 5 seconds up front and 5 seconds for the threaded version. And now we're going to come down here. We're going to wait for the threads to finish. We're going to see when our thread ended, just so we can see how long it took. And then we're going to print out the response. So we can see right here, without threading, it took 5 seconds. We're running 5 processes that sleep. They're not in parallel. So we have to wait for each one to finish. That's going to take about 5 seconds. Here, we're running 5 threads. Each one is going to sleep for a second, but they're sleeping for 1 second at the same exact time. So technically, no matter how many processes we start up, no matter how long, no matter how long this takes, like you can imagine this being like an API call or something. No matter how long this takes, if they all take 1 second, and we're doing them threaded, the entire process is going to take 1 second. And we're done. That's all you need to know. So you can throw anything in a thread you want to. You don't have to worry about it. We don't need sidekick because we can just spin up threads. Except for threads get pretty tricky. So here we're going to start with X outside of our thread. We're going to start 5 threads that each add 1 to X. Typically we'd expect that X is 0 here. We're going to add 1, X is going to be 1. In the next thread, X will be 1. We're going to add 1, and then after addition, X is going to be 2. So here we're going to print out the actual value of X after all the threads run, and we're going to wait for them all to finish running. So what is our expected total? So here our threads ran. We can see that they're not really running in order. See, the first thread actually the first thread to start and finish is actually the third one we started. So they're never guaranteed to start up at the same time. But the funny thing is that thread number 4 started up right here, and X was 2. It adds 1 to X, and then it prints the result of it, like the new result of X, which right here is 4. Which, even though we got the right total, it's really weird. It gets weirder when you do different Ruby versions. So here we're just going to have 5 threads adding 1,000 elements to an array. So each thread will add 1,000 elements. So we're going to just check the size. So in Ruby, it seems to work pretty fine. But what about JRuby? We can run it again, and we get a totally different result. I mean, we're not even close to 5,000, and it's never going to be the same. It's not deterministic. And if you want to stop here, you're welcome to leave. So here's what's going on. In Ruby, or JRuby, we got 5 threads adding 1,000 items. But JRuby, because it's built on JVM, I'm not fully qualified to talk about why this is, but it's truly parallel, meaning that all threads will be executing the same chunk of code at the same time. They could be accessing the same data at the same exact time, only one process. Some of our elements get dropped off because only one process can win in that situation. So whatever the last result, like 225 of them, happened at the exact same time, so we ended up losing some of our elements. The MRI version did the exact same thing, except for MRI uses something called the global interpreter lock, which means only one thread will be executing array.push, which is that we're adding nil items at any given time. Only one thread can actually do that, which is why we got 1,000 items, because they're all trying to do it, but only one can do it at a time. We end up with no corrupted data, but a lot of questions as to why that is. So what's the GIL? It's a lock on the CPU resources. It's specific to MRI, which was what pretty much all of us use. It ensures that only one thread will be executing MRI Ruby code at any given time. That is the C. That is the native Ruby code. The parts of Ruby that are implemented in C. It's not a public API, so the GIL is something that's private. Can only be called by the C code. But it gives us a guarantee that our operations are atomic for those things, which is why if you think about our X model, we got 2 plus 1 equals 4, but the total ended up being 5 because the X plus 1 operation is atomic. It means only 5 things happened. We added 1 to X 5 times, you get 5. For non-native MRI code, that's our cool library or our C extension. The guarantee is up to you. I mean, this is what we have to do for the JRuby example. And also, this is tricky. We'll see why. It also ensures that all threads running have a chance to have an equal chance at running by switching execution somewhat randomly between threads waiting to execute. So our 5 threads could be, one can start executing, and then the next one will be able to be executed. So it can't hog up all the resources. They're not all waiting on one thread to complete. Like we'll see, this could literally happen at any point. We'll pause, tell the other thread to run, then it'll return the lock to the thread that it paused. So I stole this from a website. We don't actually see the code for this, but imagine this is thread 1 and thread 2. They're both running this code. We've got, imagine like a sheep instance variable, and we're seeing if we have sheared that sheep. And then we're going to shear it, and then we're going to set it to true. So here's what happens with the GIL. You have a sheep. The first thread that gets it is the red one. It checks if the sheep, if we've sheared the sheep yet. It hasn't. All right, let's shear it. Except, you know, the GIL is going to interrupt us. So we're literally shearing it, and then the GIL says, all right, it's time to stop. We're going to give execution to this thread. The blue thread starts to, because it's running the same code, it also checks if the sheep is shorn. Well, we haven't set that to true yet, so it says, okay, the sheep's not been shorn. I'm going to start shearing it. So it shears the sheep. It sets it to true, which I guess means that the sheep has been, shorn. And it's done. So the GIL gave this thread enough time to run. So then it gives it back to thread A, or the red thread, where it also shears the sheep because it's in the middle of shearing it. It has no idea that the sheep has now already been shorn. I hate that word. And so it's going to shear the sheep, and it's also going to shear the sheep. It's going to finish executing, and now we've sheared the sheep twice. Does that make sense to everybody? Okay. Now I want you to imagine that this is your business charging somebody's credit card. So, I mean, you can imagine not just that situation, but there are a lot of situations where you don't really want to do something twice. There's a lot of ways around it that I don't necessarily get into. There's a lot of like really specific thread stuff to help you do that, but we're going to do some of the basics. So we're going to fix this with some of the standard lib libraries, and one of those is going to be our Mutex. The simplest explanation for Mutex is the GIL, except for it's a Ruby class that we get to use. It's available to JRuby, MRI, all of them. It creates a lock on all threads, no matter how, 5, 10, 20, 1, that share access to the same Mutex instance. So here's an example. This is just our array method we just did for JRuby and Ruby. We've got a Mutex now. And we've got an array. It's the same exact thing, except we're adding this Mutex, and we're calling mutex.synchronize. Now, what does that mean? That's what the GIL basically does. This is saying I'm going to lock access to the functions we're executing, to the logic, to the code we're executing inside this block. So now, only one thread can actually insert a nil item into an array at a time. With MRI, we didn't have that problem, but now if we happen to be running JRuby, it's going to work. I should really start going. So thread 1 starts running the block. Thread 2 also starts running, but sees the lock is held by thread 1, so it waits for that lock to be released. Thread 1 is done. It releases the lock. Thread 2 is allowed to continue. That's basically the GIL. If we go back and now run our safe, our safe example, our new Ruby example, we can see that they both work. We both get 5,000 elements in the array. So it's really helpful when you're doing that kind of thing. And we're done again. Except for there are some pitfalls. There are a lot of things that happen like we've seen. Two of the main things we're going to talk about are deadlocks and safe variables, which is that, I guess, that X example we saw at the beginning. Deadlocks occurrently try to acquire a resource lock that will never, ever, ever be able to be released. So our mutex above locks access. Well, here's an example. We got a mutex. We're going to add, we'll just call it a queue. It's just our queue. It's just an array. We have two methods. This pushes many items. It locks. Push many acquires a lock to ensure that we have safe access to adding many items. So if we call push many, we get all the code in there executing as a lock, so only one person can do it. But if you notice, it also calls push. It uses push to add items to the queue. We could obviously not do that. We could just do the variable way, but the point is now we have push, which also has a mutex. It's sharing the same mutex. So inside this mutex, we've got a lock. We've got the push method also asking for a lock, even though that lock has already been acquired. It's wrapped inside itself. So therefore, it will never be able to obtain that lock because it's currently locked. So push will end up waiting forever. Because it's the same thing, Ruby's smart enough to know it'll raise an error when this code executes as a deadlock error. So how can we fix this? There are two ways. These are, we can create two mutexes and just use them, use one for the push mini method, one for the push method. Or we can include what this was a monitor mix-in, which basically abstracts knowing whether you're actually inside a lock or not. So if we're synchronizing up here, but the monitor mix-in, which is a standard Ruby library, knows that calling a nested synchronize is unnecessary. So it won't do anything. So now we are going to thread safe variables. So here's our example with the weird addition. Remember how threads share memory? That's how all the threads had access to that X variable. This is kind of a contrived example, but let's say we have an app that we're setting, like for each request, this might be our Rails app, we're going to say, okay, the request is started, here's the current user. This is going to be the current user for the whole request lifecycle. And then we've got some other method in our app where we're going to update the current user, but here we're just going to print which user we're updating and whatever name we're going to set it to. We're going to set it to like a list of names, and then just imagine that this is a multi-threaded web server like Puma. So these servers are requests, and each request in Puma is going to be sent to a new thread or something like that. And these threads are your controllers responding. So the first thread is responding to the user ID, so it's going to set user ID to the current user. Then it's going to do some work, saving to the database, checking stuff. The last thing it's going to do is finally update the current user. Here it doesn't really matter. We're just setting a name based on the index. And then we're going to wait to happen. So again, we're just simulating some kind of global context. So we're going to run our code. And what we noticed is that though each method or each thread ran and updated, we got a new name. We got 5 names here, so we know we got 5 user IDs, 5 different threads. They're all updating the same user. Again, this is kind of contrived, but we do it again, and it's not even the same user. It's a totally different user, but they all get the same user ID. They all end up doing some hard work, and in the meantime, so what happened? For each thread assigns a current user, then it does its work. But because the assignment happens pretty fast, we end up with 4 threads that are doing extra work that have already assigned a current user. And when they're done, they're like, hey, the current user is already gonna be the one we set. We don't have to worry about it. So then they update the user, and the 5th thread comes in, which is the last one to assign it, and says, while all the other ones are sleeping, it says, okay, I'm going to set it to my user. While they're sleeping, and they all end up updating the same user. Why is that? Because we've modified this global variable right here, which is accessible to our whole application. And the last thread to start is going to be the last one to determine what the value is equal to, which is pretty tricky, but this is like a pretty basic example of unsafe thread unsafe programming, I guess. So what's the fix? We're going to use this thing called thread.current. It is a thread-safe atomic hash. We can use assigned values to the current running thread only. It allows us to enable thread-safe variable access, especially when the class storing this information knows nothing about how our application is running. What if you want to run, what if that app was a gem or something, and I wanted to enable you to run a multi-threaded version of my gem? You can or can't run it without threads. This method right here allows us to do that. So the only change we need to do is we added a current user method, which fetches the current user from the hash, the Ruby hash, in the current thread. It's almost like the current thread's cache, its own global, you can stuff its own state. So if we go, I didn't add code, but if we go back to this method, each one of these is the current thread. So that hash is new for each thread running. So that current user will only be available to thread 0 and then thread 1. They'll each be different. So when we run our code again, we notice, threads are out of order, but we got 1, 2, 3, 4, 0, 1, 2, 3, and 4. That's just a small example of thread unsafety. So here's an example of when you might want to use threads. So you have 5 URLs. This could be 5, just imagine 5 URLs. We're going to spin up 5 threads in like a rake task, and we're going to fetch 5 URLs, wait on all the threads maybe at the bottom, and now we've got really fast, data fetching from however we're going to do it. Or you've got a producer and a consumer thread. You only want to run process for them, and this one just somehow creates jobs. We're going to use Redis. We're going to add random things to the queue, and this one's just going to go on forever trying to pop those random things from the queue. Another simple example. They really aren't so bad, but there are a lot of pitfalls. So most of the time you don't really have to worry about this stuff. If you're using Puma and you're using Rails, you're already writing multi-threaded code. You just haven't, either you know that or you haven't realized it. So it's not as scary as you think. If all of Rails is running threads safely, it can't be that hard. Some other topics if you're interested, there's a queue class in Ruby, which is like a thread safe first in, first out array. You don't have to really do anything. You automatically get thread safety with that. There's a condition variable which y'all can read up on that if you want. I still don't really understand how that works. It's almost like one process asks a condition variable if it's ready, and then another process will signal, from over here that it's ready. So it's almost like a mutex where it's not happening inside a block. They're waiting on the releases. It is. Sweet. And if y'all are interested, the best way to understand about how threads work, period, is this website right here. Nobody understands the GIL. I certainly didn't. It's a 3-parter, if you got the time, but it really goes into how Ruby, MRI specifically, is able to schedules your threads to run and how the GIL works. So yeah, that's it.
This video has been sponsored by Rieta Incorporated. Learn more today at rietta.com.